consider not just the water, but also the debris-laden water, debris flows and debris floods. That was a really important point, and it's one that somebody asked me a question about this morning. The question was, are there methods for doing this? What are the methods? And there are. So there are established equations that we use for estimating the loads from debris flows onto structures. So for example, if I showed it actually for this Chikai debris flow barrier example, where I had a little diagram showing that we have impact forces on the concrete structure. And there's a common equation that's used for estimating the impact force on a structure from a debris flow. And I can provide to you the publication that describes that. But basically you take the density of the flow times the velocity squared. That's the main component. And then there's a multiplier coefficient for that. Yeah, depends on what details that you can learn about. So we do have methods. The methods exist. So that covers the impact pressures. But the other key component is understanding what is the discharge, right? So if you have a bridge opening, if you just have the 100-year water flow go through, that has a value, and you can estimate that value using common like hydrology methods, right? But for a debris flow, the discharge is going to be much higher than it is for a clear water flood, right? And there are methods for estimating the peak discharge of a debris flow, but I think that they are kind of specific to a region. And from my understanding, I think there's still work to be done for this region to understand really how to take a clear water flood and scale it up to the size of a debris flow. So I think there's more research. That's a hazard characterization work that needs to be done. And then the next thing is, it's important to understand the aggradation that would happen beneath a bridge, for example. So in some settings, you are in a steep and narrow section of the river, and during a debris flow or a debris flood, you will have erosion. But in other areas where the river is flatter and wider, that's where we have deposition. And when we have deposition, even if you had a sufficient opening initially for all of the discharge to pass, if you have deposition during the event, it makes the opening smaller, of course, right? And what we use for estimating that deposition is numerical models that look at how likely the material, or it can estimate the depth of deposition that would occur based on the confinement of the flow, or the width of the channel, and the slope of the channel. So the message is that there are methods that exist for doing all of the things that Dr. Vishnu suggested. So follow up with us and we can provide more information after. All right, with that, I'd like to go back to the group exercises. We had a potential failure mode. And that potential failure mode was that we could have erosion of the foundation of the dam caused by internal erosion and piping, and that would cause our dam to collapse. So remember, the steps of this failure mode, the detailed description was, first we would have a debris flow that fills the basin, and then that, because the debris flow fills the basin, we have water now seeping underneath our dam, and we don't have adequate filters beneath the dam. So because of inadequate filters, we start to have movement of the fine-grained silt and sand particles, and that seepage that's moving those fine particles creates what I'm calling a pipe, or a crack, or an opening under the ground. Now, as that pipe begins, it's allowed to continue to grow, so that pipe gets bigger and bigger and bigger, and it goes all the way, the pipe is so big that it causes the foundation to collapse beneath the dam. Now we have our concrete dam on top of that, and the concrete dam, it also cracks and falls into that hole. And when it falls into the hole, the debris flow passes down past the structure, it floods downstream, and the flood is large enough that it spills out and it damages buildings and it kills people. So this is the failure mode that we described. This is a detailed description, and I think it was very well done. I think this is a great detailed description of this failure mode. So now we're going to talk through what are we're not going to talk through. In your groups, you're going to work through with your group. What are the opportunities to break this chain of events to prevent this failure mode from occurring? And so for each of these rows, each of these items, see if you can come up with, say, 1 or 2 ways to stop the chain of events. And I'll say that it may not be possible for all of them. So for example, maybe you can't stop the debris flow from occurring, but for some of these others, there's going to be clear ways that you can reduce risk. So begin with your group. Here they are. You have several minutes now to write ways that you can reduce risk at each step. Ready, go. Okay. Yeah, let's go. So I don't want to necessarily go through it step this chain and prevent this failure. So we have the microphone here. What is one idea that you have?
Some of the preventive measures can be allowed previously. They can be for control of debris flow. There can be provision of check or detention dam at upstream, and we can increase the length of flow path. Also, there can be provision of drainage blanket and chimney drains at downstream. Also, there can be provision of filter media. Additionally, there can be provision of seed pile for increment of flow path. And to control flooding, we can change the land use pattern at downstream.
Change the land use pattern downstream. Yeah. Okay.
To control flooding.
Okay, great. So, yeah, that's a good one. Yeah. So I'll start. This happens, and we manage the risk by managing these items here. So you could prevent the flooding downstream by looking at the size of the channel and having a channel downstream that prevents the flooding, or you could protect the buildings so that the people aren't killed. So, or you could use land use planning, I guess is what you said. So you could have land use planning downstream. That protects people from this failure mode. Okay, from another table, can another table, raise your hand, give me another way that we can reduce this failure mode?
I don't know it will be practical, but for the first point, I have noted some solution. Provision of camera or sensor upstream to monitor the large landslide upstream of the dam. I don't know how feasible it will be. Provisioning of camera or sensors upstream.
Okay,
For the detection of large landslides.
to put cameras or sensors upstream.
For the detection of large landslides so that we could have some time to prepare for the
Okay,
failure of the
that's a
dam.
great example. So let's discuss that one more. So if you had so that would be an effective way to evacuate people. I agree. That would be an effective way to evacuate people. But if we're speaking of the failure mode as only collapse of the dam, would that method of having an early warning system, would that help to prevent the collapse of the dam?
For this, I have written one point that periodic inspection of the dam should be done and routine maintenance is mandatory.
Routine maintenance of the dam? Okay. How would the routine of the maintenance of the dam, which of these items would it affect?
Now we can monitor that our filter materials are working properly or not. And if this is not working, then we can construct check dams and we can replace the filter material with proper materials as per the site conditions, analyzing the geotechnical analysis.
Okay, so that's a good one. The filters. Right? In order for this piping erosion to occur, we have to have a poor filter. Because if we have a good filter, then this never begins. The process never begins. So right now, if we're in the process of designing our structure, we can say, oh, if we want to prevent all of this from occurring, we must have good filters. And so then we can say, well, we need to do more work to properly design the filter and be confident that during construction, the filter gradation is what we designed. Yeah, so we can solve this issue by constructing good filters. Yeah. Okay, is there another table? Another idea? What are some other things on these other points? What else could we do to reduce?
Yeah, I
the
think
change?
construction of a small scale check dam upstream to main dam itself to decrease the debris flow volume.
Okay, so if we were to build a smaller check dam upstream, then we would that would stop this first item. Is that what you're saying? We wouldn't have the barrier
Yeah,
filled.
it will decrease the volume of debris in main dam, I think.
And then yes, yes, that would be possible. I agree. But I think maybe you would have then the same failure mode potential just moved up to the first dam. So you would really have some of the same issues but at a different location potentially.
Okay, then for problem number 3, I think insertion of seed pile to increase the length of seepage path.
Great
So that-
idea. A great idea. Okay, so we can reduce the seepage gradient.
Yeah,
So if we increase the seepage path, then it reduces the seepage velocity and the gradient, which reduces the material or the ability of that seepage to remove materials. So that's a great idea. So we can increase the seepage path length with a sheet pile so that we don't initiate a pipe. Great one. Yeah, go ahead.
So for the point 3 and 4, I think we should decrease water level by discharging it through gates and spillways.
That's right. So it could be that our structure actually is controlled by this failure mode, right? That we realize that in the foundation there's a maximum amount of head or a maximum height of the water behind the structure, and if it was larger than that, we could have seepage underneath. And so we can limit that seepage or limit that head by adjusting the height of the structure. That's what you were describing, I think, yeah? Hold on.
So I'm saying that we should decrease the water level of the dam.
Yes.
Water level.
By having a spillway, I think. Yeah,
Yes.
that's right. So we can adjust the height of the spillway to limit again the gradient of the seepage.
If you start building the pool, if the collapse starts, the water level's been drawn down. Then maybe it
Okay.
decreases the likelihood of it not.
Yeah. Other ones? Anyone else? Okay, so now we have a number of options that we can use moving forward as we design a structure, right? We can think about land use planning downstream for the debris flows that pass the structure. We now understand the importance of designing good filters, and we can do things to increase the seepage path length. So I'll start now with back to the presentation.
We talked about the first, second, and third points.
Yes.
That there are different alternatives to stop or to decrease those parameters. So what I was thinking is, for example, in a worst case scenario,
Yes.
we use geotextiles or we use sit piles and everything that's possible
Yes.
to stop the seepage. But still we have a seepage and the piping effect occurs. And due to the piping effects, if the pipe starts to get bigger, how can we stop it, or how do we manage that? The fourth point.
Yes.
So I didn't know what to do.
Yes, so the pipe begins, right? It takes time for this to develop. And that's an important point, that it doesn't happen instantaneously. It's not like a debris flow hits it and it collapses. It's a process that begins and the pipe gets bigger and bigger and bigger. And so in some cases, you could have equipment and materials staged downstream of the structure that can respond in case the pipe begins. So if you have a barrier, you have a structure, you have seepage underneath here, let's say there's debris there, or sorry, the foundation here. The erosion it begins here and it starts to work its way backwards. right? And then you get collapse of these materials in. Well, if you have equipment here, you can start to place material here during the emergency so that you don't get as much material eroding outwards. And so you can have an emergency response that begins to actively prevent the pipe from getting bigger by placing coarse material over the downstream where the water is exiting the ground. So that's a possibility. It's sort of an emergency action that you would do at the last, it's the last option that you have, but it is an option. Sure. Anything else? Are there other questions? Okay. These uncertainties so that other people who come in the future can follow what we've done. And the way that we do this, the simple way, is we separate our uncertainties into two categories. We call one category the adverse factors and the other the favorable factors. So adverse these are the uncertainties, or these are the factors that could make this failure mode more likely to happen. And then the others these are things that could make it less likely to happen. Okay? So you start to try to understand, like, is this actually possible or not possible? So when we take the example that I was using before of a debris flow during construction that kills a worker, the factors that make this failure mode more likely are the fact that there's workers, they're down, let's say they're building the formwork for the base of the concrete structure. In that case, they're wearing hearing protection because there's loud equipment moving. And even if there was an alarm, they have their heads down with the hearing protection and they're working, they wouldn't hear the alarm. So this makes it more likely that this failure mode is a real thing that could happen and kill somebody. Another thing that makes this more likely to happen is the fact that there's workers, they're confined in the canyon, and it's difficult to climb out to higher ground. So this is like, yeah, this is real. I believe that these things could happen because of these factors. On the other hand, a factor that makes it less likely for somebody to be killed is that I happen to know at this site that there is a rainfall monitoring system and an evacuation system. And we know that also that the site is going to be shut down when it's raining heavily, right? So the point of this is to try to think about at each step, remember we had our 5 steps or 7 steps, is it actually possible for these things to happen? And you write down what makes it more likely, what makes it less likely. So for our failure mode, let's go step by step. With your groups, let's talk about what are the factors that make. So you could do this for each of the steps in the chain of failure modes, but let's talk about the collapse of the dam itself. So think about the design of this dam. So we have a concrete dam that has bedrock on the sides and a bit of sediment in a narrow section in one part of the dam on the foundation. So talk with your group about what are the factors that make collapse of the dam more likely, and what are the factors that make it less likely? Is this clear? You're just describing the uncertainties. Talk within your group about whether you think that a concrete dam that has rock on the sides, is it possible for the dam to collapse or not? This is what you're writing. And you can make arguments. So one person says, yes, I think it can collapse. I think it can collapse because, and you write down why. And then the other person says, no, I don't think it can collapse. It won't collapse because, and you write down why. That person makes their argument. So there's not a right answer or a wrong answer. You're just collecting the arguments that people are making for why it can collapse or why it cannot collapse. Ready? Go. A concrete barrier. It's mostly bedrock, but there's this one channel of alluvium underneath. So what are the arguments for collapse of the dam? What are the things that could make the collapse of the dam more likely?
Due to overturning of the dam, bearing failure, sliding failure, translational failure, upthrust, and seismic activities. And not likely component are thermal effect, fire hazard, liquefaction, and wind load. Thank you.
So that was a description of storm failure modes, and you separated them into categories of what you felt was likely and unlikely. Yeah. So for the specific failure mode of erosion, so if we imagine that we have a pipe that forms here underneath our structure, and it erodes away our dam. So let's say we have piping that occurs here. So we have a large pipe that erodes all of this away. What would be the consequence on this dam? Yeah, it might. Maybe the dam could it could crack here. And then what would happen if it cracked there? Yeah, maybe it falls down. So maybe instead of there. Oops. So maybe instead of that, it falls and fills in like this. It's concrete. So what are arguments? Do you think that this is possible for this mechanism to happen? We have seepage, a hole, and it falls in? Maybe. What are arguments for this happening? Any ideas? Somebody raise their hand and we'll bring you the microphone. What are arguments against? What are arguments that prevent this from happening? Ideas? Yeah, go ahead.
Happening.
Yeah, so one argument is, remember, if when we close the basin, we have poor filters, and we have seepage that makes that pipe. The pipe grows very large, and the foundation collapses. Now the question is, could we have collapse of the dam? And we're finding that, well, not really, because even if we have that large pipe open up, the concrete dam is concrete, and so it's able to bridge that gap potentially. Right? So that's the type of investigation that we're working through as we work through this potential failure mode analysis. Are there any other ideas of what could make this more or less likely? And if not, I'll move on. Okay.
Drugs.
Yes, okay, that's a good point. That's a great point. So you could have, so I've assumed that you don't have any sort. But I think the point you're making is that potentially the bedrock is not strong. It could be very weak, and if it's weak, that could make this type of failure more possible, because then you don't get the bridging effect from the concrete that was mentioned, right? So again, it doesn't have to be that there's an answer to this, but you're listing the factors. And so if you decided, well, maybe that's true, maybe that the bedrock is not strong enough, what would be a next step that you could take to try to investigate that question? I'm putting you on the spot.
The geology of the dam site.
Yeah, that's right. Yeah, so maybe we decide, well, if the bedrock structure was very poor, maybe there was a bedrock structure like this that allowed or facilitated this failure, you could go and do an investigation of the bedrock, maybe some boreholes and core samples to try to understand if it's possible for the bedrock to fail into this opening. So this is an outcome that you could have. Is there anything else? Any other comments? Yeah.
Design phase, we can apply remedies for this kind of failures, because during the design of concrete, we also deal with the shear force. And the shear reinforcement within the concrete structures are there to resist those sort of forces. So this is not likely to happen. I think so.
That's right, yeah. So in the design phase, you can incorporate things into the design to prevent this from happening, or you can do the investigation to show that it's not possible to happen. Yeah? That's good. Yes, I'll move on now. Actions. You've thought about your uncertainties. The next step is to determine what actions are you going to take. So you have to then identify which risk reduction options are you going to actually apply. And I'll say that, sometimes you're going to apply actions that reduce risk. So for example, sometimes you're going to do something like design a better filter or install a better filter. That would be an action that costs money to reduce risk. Other times, you might say, well, the action is, I don't know if the bedrock is strong or weak enough to prevent the failure mode. So your action might not be to reduce risk, but actually to reduce uncertainty instead. So that's what this graph shows here. The x-axis is risk. So sometimes you're at low risk, sometimes high risk. This is uncertainty. In some cases, you have low uncertainty. You know a lot of things. Other times, you had high uncertainty. You don't know much. So if you have something that's low uncertainty and low risk, usually you can tolerate that risk without taking any more actions, right? But if you have something that's low risk with very high uncertainty, well, you don't know actually if you're really low risk or not because of the uncertainty. So oftentimes there you're going to do something to reduce the uncertainty. You're going to go and collect more information. On the other hand, if you have a very high risk but a low uncertainty, so then you're confident that you have high risk, then you're probably going to take action to reduce the risks. Right? So that's what you're thinking about when you're trying to determine what your next actions will be. So for this Chikai debris flow barrier, as we worked through this process, we looked at 101 failure modes, and we looked at them in a very detailed way, as you have done for this one failure mode. We decided in the end some things that we needed to do to address our failure modes. One was we installed a monitoring and alarm system. And the purpose of that system was to protect the construction workers during construction. Another thing that we did was we installed what we called these parapet walls, these walls that were on top of the structure. We put them there because we wanted to protect the foundation from flows that overtop the structure. So we forced the flow into a spillway that spilled onto rock so that we didn't get erosion of that soil foundation. Another thing is we realized that our drain system, we talked about piping, that's what we've worked through as a group. We learned that our structure was somewhat susceptible to piping, and so we increased the size of our drain system to address that issue. And then another point was we didn't know if the foundation materials were compatible or not, and so we did additional investigation during construction to make sure that we have adequate filters. So these were actions that we listed at the end of our potential failure mode analysis for us to carry out to show that we were managing the risks. All right, we have about 20 minutes left, and I'll go into the last section now. Are there any questions about the potential failure mode analysis before I go into this last section? We're almost done for the day. Are there any questions? Yes, microphone.
You had drawn force, partial safety factor. You had shown a chart, right? The probability to speak. So, do we do we create those, or do we already have those safety, the partial safety factors when we are designing? You said that we design and we see if the safety factor, how to put it, is it in the range of failure, or is it beyond? Yet shown that one picture.
Yeah, let me explain that one. What I was trying to is there is still a probability of failure. And so this method that we just described is an alternative way of looking at failure that has nothing to do with the safety factor. Yeah, so even if you do a calculation that shows an adequate safety factor, there's still ways for the structure to fail. So you can't say that because the factor of safety is adequate that the dam is entirely safe. That's the point that I was trying to make. Is that clear? Okay. Any other comments or questions? No. We need to be reduced. Or how do we decide which of these actions we need to take? How do we prioritize? And the method that we use is we call it semi-quantitative risk assessment. And we use this method to decide if actions are needed to manage the failure mode. And we use this graph. This is a really helpful tool for us. So on the x-axis is some measure of the consequence of the failure. So this could be the number of fatalities that's caused, or it could be the cost of repairs. And on the y-axis is the probability of failure. So this is how likely is this failure mode to occur. And these lines represent some measure of tolerable. So we'll say, well, if we are above this line or above this line, then the risk is too high. We must do something. But if we're below the line, that means we have a small consequence and a small probability, then the risk is low enough that we don't need to take action. This is how you can decide whether to take action or not. Now, clearly, you don't need to take actions if the failure mode is not physically possible, right? We don't need to do anything. You don't need to take actions if the risk is clearly acceptable. So, for example, we were worried about a tourist falling off of the top of the structure. Well, we've already designed railings. We've already decided that's acceptable, so there's no further work that's needed. But for all of those other failure modes, even the piping one that we've discussed, how do we decide if we need to actually take the action or not? How do we decide if it's worth the investment? Well, this is the method that you can use. And so, if you have, say you start with 101 failure modes, you decide that 80 of them are not possible and some other 10 of them are acceptable, then you have some remaining that you need to manage. And you can use that same graph just to plot each of your failure modes. So each of these dots represents one failure mode, right? So this one could be that you have, say, overtopping of the structure that has this probability of occurring, and if it overtops, it could kill this many people. So this one is a high-risk scenario, right? It's high probability, high consequence. Whereas down here, this could be another failure mode that has a low probability of occurring and a low number of fatalities, so this is a low-risk scenario. So these ones here, the high-risk, these high-risk ones are the ones that you need to focus on, and these ones you wouldn't focus on. It allows you to prioritize. Another way that you could do it is by using these risk tolerance lines. You plot them, and you can say if you're above the line, these ones you must address, and these ones you don't need to address. Now, what I'll describe quickly is how do you decide where to plot these dots. That's what we'll learn about just now. Well, the point I was trying to make is that, you can have two failure modes. One mode that, like this failure mode here, that results in quite a high repair cost. But that same failure mode, even though it doesn't have a high repair cost, it can have a low number of fatalities. So you can look at different types of consequences with this method. You can look at economic consequences or life loss consequences, and you'll get different answers depending on which consequence you look at. So often you would do it for both types. So this semi-quantitative risk assessment is a much shorter process than what we just went through. There's only two steps. One is to estimate the consequence, and the next is to estimate the probability. So back here, you're just estimating the consequence is on this axis and the probability, and that allows you to plot each of these dots. You just need those two values to plot the dot. So the first step is to estimate the consequences. So the point is we need to create a consistent basis for doing this, and we need to select which consequence we care about. So it could be the life loss that occurs if it fails, it could be the repair costs, or it could be the economic losses downstream. So you choose one of those consequences, and then you just try to estimate the consequences to within an order of magnitude. You have to understand that it's a very uncertain analysis, and so you're just trying to get to a general estimate of the consequences. And then the next step is to estimate the probability of the failure occurring. That was the y-axis. And for this, similarly, consistency is key. So you need to use the same method for every failure mode so that you're able to compare them. And we're going to use that failure mode description in order to make our estimate. So what we do is we make an event tree or a risk tree, like Emily described this morning. She described the step-by-step approach. And then you can assign a probability to each of those steps. And when you multiply them together, you get the probability of it occurring. So for this example, if we were to estimate the probability for this, remember I talked about this example early on where we have woody debris that's blocking the spillway. So now we have water flowing around the structure. And that's causing erosion of the dam. So the event tree, that would correspond to that. It begins with the dam. So the failure mode that you describe as dam is outflanked due to woody debris blockage of the spillway. That's the description of the short description of the failure mode. Okay, so the steps are, we have flood that carries a large volume of woody debris. So we estimate that a 1 in 200 year flood would carry that debris. So that's the first value. Now, will that volume of wood block the spillway or not? We don't know. We think maybe yes, maybe no. So we'll assign a 50% probability to that. Then we get to the next one. If the spillway becomes completely blocked, will the water overtop or outflank the dam? Or is it able to pass through without the dam failure? And for this particular dam, we can investigate and say, we think that if the spillway blocks, it's very likely that the dam fails. So we would say there's a 90% chance of this occurring. So now when we assign those values, so we have 1 in 200 chance, a 50% chance, a 90% chance. So if I can write. No? Here?
No.
That one?
Right most forward.
So remember this morning Emily showed that you kind of choose your way through one of these event trees to calculate the probability of failure. So can somebody tell me, or maybe talk to your group, calculate for me the probability of failure using this event tree. Can you do that? I'll give you 1 minute. What would be the probability of failure?
You have already calculated.
I already calculated. I already showed the answer, yeah. You got it right? Yeah. Alright, this is how you would do it. Who got this number? No, wrong one. It's not right. There, this one. Okay. Did everybody get this here? The answer was shown on the screen? Yeah? Okay. All right, we'll do one more. So let's look at the probability that a debris flow during construction kills a construction worker. So the probability of a debris flow occurring during construction. Let's say that's 1 in 100. And then the construction only happens during the day. So the probability of a person being present during the event is 50% because they work a 12-hour shift. There's workers, and 12 hours at night, there's no workers. Now, the probability of a worker being in the channel when the debris flow occurring, well, only about 30% of the work is happening in the channel. The other 70% is happening up out of the channel. So that's where this 30% comes from. And then we know that we have a warning system, and we know that we have ways for workers to get out of the channel because they have staircases. So we'll say if the debris flow occurs and the worker's in the channel, we think there's only a 10% chance that the worker would be killed. 90% chance that they would be able to escape. Okay, so please calculate now the probability that a worker is killed using this event tree. Yeah? Everyone sees it on the board already? Yeah, too late. Yeah. All right. So now, if you calculated, everyone should have calculated this value. No? Try it again. No? So does everyone recognize that value? That's what you would have calculated. So then you can plot that on this axis. And then if you can estimate that there were always between 1 and 10 workers at the construction site, or say there was 20 workers at the construction site, but you assume that only half of them could be killed, then you could say, well, this is the range of where people, of the number of fatalities, and then you can plot onto the plot what the risk is, right? So there's a high probability of 1 to 10 fatalities. So you can plot that. So we're about out of time, so I'm going to go just skip the next one. But you can do the same thing. You can do the same thing for other failure modes. So for internal erosion and piping, for example, this is one that we worked on today. We've talked about all of these different steps that we need to happen. So you have to have a debris flow that fills the basin. You have to have drains underneath that are not big enough. Then you have to have internal erosion and piping that occurs. And then there's no equipment available to stop the progression of the pipe. And then you have to have the whole barrier collapse. And when you assign a probability to each of these and multiply them together, you get this really small number, 4.5 times 10 to the minus 6, which you can plot here. And even if that failure mode occurs, remember the top of the barrier only settles a small amount because it's concrete, right? So it doesn't disappear like an earth dam. It only settles a few meters. So then when the debris flow passes out, it's actually very small debris flow. So in that case, it doesn't kill very many people. So that failure mode would plot here, right? So now when you compare these, let's just look at the fatalities. Our failure mode of killing a worker plots way up here, and our failure mode for the piping plots here. So this one is the higher risk failure mode. And so this is where you would invest money, and this one you would not need to invest money. That's how you compare your different failure modes. Now, you can, if you have 101 failure modes, and in the end you want to compare them, you can plot many of them on the same graph to understand which are the most important. And then I'll leave you with this. This is the template that you can use to do this whole process that I presented this afternoon. So you'll find this in the materials that we've shared with you. This comes from the organization in the United States who manages dam safety. They use this template. So they list the potential failure mode. At the top, this is the number and name of the failure mode. Then they describe each of the steps. Then they describe the factors that make it more likely, the factors that make it less likely. Then they describe the probability of failure, the reasons why they assign this probability of failure, and then the same for the consequence. So this is a template that we have used where we'd have one sheet for each of the failure modes. And you work through all of them this way. And just these are some resources where if you click on these links later, it has much more information about how to do these potential failure mode analyses. And that's it. So yeah. 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 So as I said before, yes, we do have methods for looking at debris flow impacts to bridges. The first is there are accepted equations that we use for looking at the impact pressure. So when you have the structure, the debris flow hitting the structure itself, the impact force depends on the velocity squared times the density of the flow. And so if it's purely water, then it has a lower density than a debris flow. And so that's the main issue. Also, debris flows tend to be very large discharge, so you have a high velocity with the debris flow. So there are accepted equations for that I can give you connections to. The other component, so that's the impact pressures. The other component is the discharge underneath a bridge. And a 100-year return period water flow will have a much smaller discharge than a 100-year debris flow, because you have bulking that happens as sediment fills in the water and makes it bigger. And those bulking relationships, they vary from region to region. I don't know what the bulking relationship should be for the Himalayas. I think that there is probably some research that exists, but there's probably more research that's needed to understand how much that bulking should be. But the other important piece is that you have bulking of the material that's flowing through, but you also have deposition underneath bridge openings. Yeah? And the way that we look at that deposition is through modeling of the sedimentation using numerical models. Yeah.